Okay, here we are with lecture 11.2, which is the next one, and here we're going to talk about the kinds of chemical reactions we have. There are 5 basic categories of chemical reactions. The first one is called a synthesis reaction. Its general formula is A plus B makes AB, and this is where we have one product coming from 2 or more reactants. The example we did in class is a flame of magnesium burning. Okay, the example that we did in class, or the example that I give you guys in the notes, is sodium oxide plus water makes sodium hydroxide, and I wish I had a better demonstration for that, but this is just kind of sort of letters to you. Another one I'm going to give you is this one right here, and this is the example that comes out of your book. A good picture of it. Okay. But the reactions are generally 2 elements, or 2 compounds, where one compound is a molecular compound, and a probable product is a single compound. For example, burning magnesium in air, and this is what we did in class. We take a ribbon of magnesium and we set it on fire, and it gets really bright. This picture does not do it justice. Turn out the lights, set this baby on fire, and it gets really bright, and it creates a sunspot in your eye, and it's really cool to do in class. And this is the formula for it. It is 2Mg. 2Mg solid plus O2 makes MgO. Notice that there's one element plus another element creating a single compound. Okay, so that would be our combination reaction. All right. The next kind is a decomposition reaction. Okay, the general formula is AB makes A plus B. Its distinguishing feature is that it is one reactant to yield 2 or more products. So it's the opposite. Okay, it's the reverse process of a synthesis. You have one thing and then it breaks apart. For example, is the peroxide reaction when you put it onto a wound. Aside from the stingy part, which is really the peroxide irritating the nerves in the wound, it also, the bubbles that you see on the peroxide is oxygen that is getting released. And it is the decomposition of the peroxide that produces the oxygen, leaving behind just, well, water. However, there's another one, and it's discovered by Joseph Priestley in 1774. And oxygen discovered by Joseph Priestley in 1774 with the decomposition of mercuric oxide. And that looks like... Okay, so this decomposition reaction is this. And this is the mercury under heat. It gets heated up, and it releases oxygen gas and leaves behind the liquid mercury in the test tube. Okay, and this is generally a single binary compound with a compound with polyatomic ion, and it will generally result in 2 elements, or 2 or more elements if it's with a polyatomic ion. Okay, and our example is heating the mercury 2 oxide. It looks like that. Push that away. Which brings us to our third one, which is a single replacement reaction. I'm going to try and do one of these for you in class on block day. Okay, the general formula for a single replacement reaction is A plus Bx makes Ax plus B, or X plus By makes Y plus Bx. And so, remember, in our normal structure for compounds, the first thing listed is a metal, and the second was a nonmetal. So this first one, A plus Bx, is a metal plus a salt. Remember, is a metal plus a non-metal. Okay, non-metal, Nm. Okay, and then those two would switch. That's this first one. And these guys over here are halogen plus metal halogen. Okay, and the X and Y are the halogens and B is the metal, and the halogens will switch with each other. Now, its distinguishing feature is 2 reactants, 2 products, with 1 reactant and 1 product being an element. This really only happens with elements. Okay? this is an equation example of what it looks like, where you have one element here, and you have one element over here, and the magnesium swaps with the sodium. That's an example. Okay, so that's the formula for it, but here is our picture example of it coming from your book. Okay, we have an element and a compound in the single replacement reaction. The element replaces another element from the compound in the aqueous solution. So here we have potassium with water making potassium hydroxide and hydrogen gas. Now the cool thing is, okay, the potassium replacing the hydrogen releases hydrogen gas, and hydrogen gas is highly flammable. And that's where you get these cool flames up on the top, leaving this potassium hydroxide behind. Okay, we're going to try this with sodium, which is, shall we say, a bit more volatile. So we're going to try and do that on block day. Okay, this brings us to double replacement reactions. Now the general formula for a double replacement reaction is AX plus BY makes AY plus BX. Now you might see what's going on here already. And what you have is a date swap. So you got one couple coming to the dance. Okay, and another couple coming to the dance. But they really want to be going out with each other. And so A over here, the metal here, really wants to be going with Y. And B really wants to be going with X. And so what happens? At the dance, B hooks up with X, A hooks up with Y, and one of them actually leaves the party together. One pair, and this is how it happens in the real world, in chemistry. This is how it happens. One of them leaves the party. Okay, they will actually leave, they will drop out of the solution, or they'll make a gas, and the gas will evaporate out. Okay, so the distinguishing features, 2 reactions, 2 products, and everything's a compound. So our example here is calcium carbonate plus hydrochloric acid makes calcium chloride plus carbonic acid. Now this carbonic acid is what you guys drink in your soda. It's an acidic drink. And this will actually break up into H2O and CO2. And the CO2 is a gas that evolves. And that's what drives this reaction, and this is what escapes. Now, here's the example given by your book. Okay, let me clean up my drawings here. Okay, and they do potassium carbonate and barium chloride. And that'll make potassium chloride, which doesn't leave the party. Those two are called spectator ions. They actually sit there and watch what's going on. And barium carbonate drops out. And if you look real close, let's see if I can expand this a little bit. This gets really cloudy right here. And this cloud is actually a solid that accumulates in such a little crystal form. It forms little crystals, and it falls out of the solution and drops down to the bottom. Okay, so that is the general form for a double replacement reaction. Which finally brings us to our combustion reactions. Okay, a combustion reaction involves hydrocarbon compounds, either CXHY or CXHYOZ, reacting with oxygen to produce CO2 and H2O. This is always a reactant. The oxygen is always a reactant in a combustion reaction. And CO2 and H2O are always the products in a combustion reaction when we're dealing with hydrocarbon compounds. Now, our examples here. So what really you get tested on with this is knowing it's a combustion reaction and then being able to balance it. And these are tricky. Okay, so we're going to balance the combustion of octane here. Well, we're going to hold on for this so I can show you guys an example of combustion. Okay, it's pretty straightforward. Okay, and voila, there it is. It's our Bunsen burner. This is the Bunsen burner, and it's burning a flame, so it has methane shooting out, CH4, plus 2 oxygens, makes CO2 and H2O. Okay, so this is the combustion of methane gas and air. When I used the portable burner on my desk, that was a butane burner, but it was still the same idea. Okay, now to balance octane, we're going to try and blow this up a little bit. So, okay, so there it is, should be bigger now. And to balance octane, we're going to follow the same rules. We start with carbon. We start with, well, we don't have any metals here. And we want to do oxygens and hydrogens last. So we're going to start with our carbon. We have 8 carbon here. We have 1 carbon over here. So we're going to put an 8 in front of that. Now the next one we have 18 hydrogens and 2 hydrogens here. Well, how do we get 18 from 2? That's a multiple of 9. Okay, so that's a multiple of 9. Now, so we're done with the carbons, we're done with the hydrogens, now let's go to the oxygens. There's 2 oxygens over here. This is the only source of oxygen. But over here we have 8 times 2, which is 16, plus 9 times 1, which is 9. That's a total of 25 oxygen. Well, it is not possible to get an exact number of 25 oxygen from pairs of oxygen. So when this happens, we need to make more of everything, because we're going to have to double this 25s, because normally we would need 12.5 molecules, but we can't have half a molecule. So instead of having 12.5, we're going to double the 12.5 to 25 oxygens. But if we're going to double that, then we're going to double everything else as well. So instead of that being 8 and 9, this is going to become 16 and 18, which will mean we need 2 octanes over here. Okay, this is not the easiest, so what I'm going to recommend you do is go back and look over what we did and try this yourself a couple times. The next example we're going to use is glucose in blood. So if you can remember what glucose is, okay, it's C6H12O6. And respiration is a form of combustion. Okay, in fact, this is where your body acquires its heat, is through the breaking apart of this this glucose molecule. We need to start balancing this one. So there's 6 carbons here, 1 carbon here. So we're going to multiply that by 6. There are 12 hydrogens here, 2 hydrogens there. We will need to multiply that by 6. Now we go to the oxygens. There are 6 here, and there are 2 here. There's a total of 8, but don't think of them as adding, because this is a big molecule, and these are all wrapped up in here. We've got a lot of oxygen O2s to play with over here. This is what we're going to need to do our balancing. So, this side, there's 6 times 2 is 12, plus 6 times 1 is 18. Well, if we take this 6 out of the equation, 18 minus that 6 is going to leave us with 12, and we can get 12 oxygens from O2. We just do that. Okay. Which brings us to, and this O2 kind of brings us to diatomic elements. There are 7 elements that are composed of 2 atoms in their natural existence. Okay, and you know what they are. We've gone over them before. They're the Magnificent 7. But to remind you, because you need to know these by now, right off the top of your head, they are hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those 7 are the 7 that are composed of 2 atoms in their natural existence. That concludes our Chapter 11, Section 2, and we will see you guys next time.